You are? Andrea, you are ready as well? Okay, great. So, to start with, I would like to say that we could, for technical reasons, not print out today's sheet, the exercise sheet. We prepared a Christmas sheet, we called it. It's not particularly pleasant, but it contains one pleasant thing, and that is that large parts of it are just a description of what the projects should be. Yeah, so what I would like you to do over Christmas is actually read what these projects would be about, and also think about what type of project you would like to embark on. Yeah, these projects we announced already at the beginning of the lecture would be like the second part of this teaching module for the mathematicians. They are just part of the lecture. For the engineers, they can choose it like an extra module. That was not possible differently. But I strongly recommend it to everyone, and it is actually it's the fun part of the course. Yeah, so these projects can be either algorithm-oriented. So you could actually just say, there was one of these algorithmic ideas that you just mentioned, but you didn't really explain in the course. I want to try this and develop it. And then you would be more an algorithmic project which implements a new method that we didn't implement yet in the exercise sheets and tests it maybe on several test examples, compares it maybe with some other method, but you would not focus on formulating the problem, but you just take some problems from what you find. Yeah? So you just take a few test problems, and then your work is really on the algorithm. You need to understand this algorithm. This is the algorithmic project. It's one possibility. The other possibility, which I also strongly recommend to everyone, because it's also a very good learning process, is what we call more an application-oriented project. So application-oriented projects would mostly focus on one specific problem or class of problems. So you say, I was always interested in, I don't know, my aunt is an engineer and she works in whatever, and she has this problem and I want to optimize it. And then you start to model the problem and find out what are the equality or inequality constraints, what are the decision variables. You detect if your problem is convex or not. You try to make it convex if possible, and so on, right? So you get more feeling about what it means to bring a problem from the real world to the mathematical optimization world. And afterwards you take, let's say, an appropriate algorithm that ideally we have programmed in our lectures, so one of the methods, or maybe one step ahead. But a standard method, you would implement it and solve your problem. If your problem is extremely difficult, you could also say, my project is only about formulating the problem, and at the end I solve it with fmincon or something like this. I would usually be favorable that you do it with an algorithm where you see everything in between, so not a black box algorithm. But let's say if your focus should be completely on the application, you could even do that option. Yeah? So there is a whole range. So developing the algorithm yourself, or using a black box algorithm but having a complicated problem and really understanding it. So this whole range is available to you, so please think of what you want. At the end of these projects, we want to have actually a running MATLAB code that actually shows that what you did, you really did, yeah? And you can show it actually here in the final presentation. And the output that we look at which we want to take as a guiding line for grading the project, is also mostly a report. So it would be a written report of 6 pages, not too long. Can be a bit longer with an appendix if you say it's necessary, can be a bit shorter, but that's the guiding line. And we choose actually a format for conference proceedings articles. It doesn't mean that your projects will become directly accepted at a conference, but afterwards, so think of this in your mind. So think this could be something that should be so interesting for others to read that they would accept it at a conference in the book of abstracts or the book of papers. But that's also just a format that gives you a nice length of the article. So the instructions we wrote down. There's one important thing. You can work in groups. We decided that you can work in groups, but only up to 2 people. Yeah, so 1 or 2. Because otherwise it's getting too diffused for these projects. Yeah. So please think about the group and the project title that you want to embark on. And if it's an application-oriented project, you could already say, I think that these and these and these could be the decision variables just in words, and that the inequality constraints could be given by this and this and this, and the objective by that and that. So that you have already some description in words where you make a first step towards formulating your problem. That is actually a way for us to understand what your project could become, and then after Christmas we would iterate with you in a process that will maybe take 1 or 2 weeks to make your project really doable. I mean, that it's not too difficult and maybe also not too easy, but usually all your projects will be probably too difficult, and then we try to make it simpler. Yeah, so in that sense, you should start to describe it so that then we can start to help you in making it as simple as possible so that it can be done in actually 1 month's time. Yeah. So this is about the projects, and the absolute final deadline at the end for the projects is February 11th. It's 1 day before the semester ends. So that means on February 11, we would like to receive these 6-page reports. So it's something which will happen in basically January and February. And the oral presentations will be on February 12th, so the last day. That's actually today in 2 months, nearly. Not 6 weeks, I think. So that is the outline of what will follow. In order to make time for your projects, we will reduce the exercise sheet significantly, so we will actually do only one small optional exercise still, and then don't have any exercise sheets. And also on the lecturing side, we will reduce significantly the amount of lectures. So there will be basically 1 lecture per week, which is a real lecture. The other slot will be for doing your projects. About the room where we do it, we could actually decide to do the project work sometimes in this room, which would be possible because you can bring your laptops, but if you think this is not a good idea, we would reserve other rooms. So is there any opinion on when you have, because we have the lecture rooms reserved, so then we wouldn't do any work, we could just meet at the usual place, but we don't have a lecture, but we do projects. Would you find that feasible, or is it not so? Would you prefer to be in a more lecture-like room, exercise-like room? You think you could bring your laptops here? Okay, then we would just do it.
How many lectures will there be in the next year?
I think about, I mean, it depends on what you count. There will be 3-4 lectures, for sure, at least. But there will be also the final presentations, which will also take place in this room, which is a lecture in some sense, but it's given by you. So there will be a slot of about 10 minutes for each project, and you will present what you did. It can be mostly based on your report. Actually, in extreme cases, you might just take the PDF of your report and project it to the slide, but you could also make your slides, which are a bit more adapted to the presentation, and that contains a few excerpts of your words. So please do not overestimate our expectations. It's only 1 month. Even though the format is in a conference paper format, it doesn't mean that it should become something that you could submit to. Yeah? It's a report, it's a project. So it can be simple and it can be tutorial and it should be simple. What we want is just to have some format which we can actually, which has a bounded size. Yeah? It's not too long, and where you get obliged to put a title, your names, section titles, a list of references, so little things that every technical report should also contain. And so it's this format that we would like you to use. Yeah? But the contents can be less severe than at a real mathematics or engineering conference. Okay, so that's the first part of this exercise sheet. Should just start thinking about projects, that they could be fun. And next, after Christmas, we would have a round where we would ask people to say a bit about their projects and what they would be. The other thing that this sheet is about is we just copied one exam question from a previous exam that I did in Leuven. It was one of the long exam questions, which is, I think, appropriate to do. Now it's investigating one optimization problem with 2 variables and 2 constraints and 1 objective, a bit like the thing that we do here at the blackboard sometimes, but a bit more complicated, where you would have to write down and decide if LICQ is satisfied, or if the necessary optimality conditions are satisfied, and so on. So it's mostly paper. It's no MATLAB, actually. So that's the good thing about the Christmas sheet. There is no MATLAB, if you think so. Okay, this sheet is now already online, or will be made online in a few minutes. Are there questions regarding the Christmas sheet? I forgot to say one thing. It will become, or it should be handed in on January 12th. So not exactly after, not at the next lecture, but one week later, on Tuesday later. Yeah, so its deadline is on a Tuesday. Okay. Everything okay? Okay, so then I'd like to continue, and my outline for the day is that we want to continue with equality constraint optimization algorithms first, and if time permits, I hope that we will already be able to start inequality constraint optimality conditions today. Okay. To recall, I want to recall things relatively directly by starting already the next lecture, because I want to summarize what we did already in an algorithm that I call algorithm 8. So we are still in chapter 12. And this was about equality constraint optimization algorithms. But I want now to basically summarize everything that we did in an algorithm, which is the basic structure of all our algorithms. And then I will look at the details. You remember in unconstrained optimization we had Newton, Gauss-Newton, BFGS. And so these possibilities also exist here. You remember we can take a Hessian, which is not necessarily the second derivative of the Lagrangian, but it should be similar to it. And so let us get the basic structure of these algorithms. And they will always choose, so this is a bit more general Newton type. With equalities, of course. And what we need to choose here is something like, at the beginning we choose an x0 initial guess where we start, and we choose also an initial Hessian matrix b0, which should be typically positive definite, right? So you need to choose primary variables and a Hessian. These were the only two things that we really needed in order to solve a system. And then of course you could have a tolerance and so on. Yeah, so the tolerance, maybe some other algorithms, parameters, but let me skip them at the moment. So you start with k equals 0, so that's the iteration index. And then you go on, you actually, before you start, you have to evaluate some quantities. This is actually the order of the algorithm. You will see makes sense afterwards, but what do you need in order to be able to solve a linear system that gives you an improvement direction? You need to evaluate the gradient of your objective. You need to know if your equality constraints are violated or not, so you need to evaluate them, but you also evaluate the derivative of these things. So let's call nabla G at x0. So this is the Jacobian matrix transposed. These three things you will evaluate. And then you can actually already compute the Lagrange gradient. So this is something I should keep in mind. So you can always compute the gradient of the Lagrangian, which will be the gradient of the objective minus the gradient G times lambda. Oh no, you cannot. Sorry, so you cannot evaluate it yet because you don't know lambda yet, right? So at the beginning you will actually always have to start this loop, but then in the loop you will actually check two conditions, namely that your equalities are, if they are getting 0, then you can stop, and if the gradient of the Lagrangian is getting 0, then you can stop. So while this is actually bigger than the tolerance, or the gradient of the Lagrangian is bigger than the tolerance, so that would be the other criterion, and this will be not satisfied anyway. So this will be, because you cannot evaluate it, you would just say this is true at the beginning. So while this is the case, you iterate. And now you need to solve the KKT system, the system that we had found before. And what we remember is that this was, you could formulate it as a QP, but we can also write it as a linear system. So it's a system where we had the nabla F here, the G here, of course evaluated at the current iterate. I will omit that. But then I have here my BK, the current iteration matrix. Here I have the nabla G transpose. Here I have the nabla G with a minus sign if you want, but actually I put the minus sign at the variable, right? And then what I get here is a pk and a minus lambda tilde k. And this pk is actually a step. You remember that was a step, while the lambda tilde was already the new value of the multiplier if we would do a full Newton step. Yeah, this was, you remember this trick that we didn't use the Lagrange gradient here, which is the thing that we want to drive to 0, but we take the gradient of the objective. This was allowing us to start without any knowledge about multipliers, so you don't have to choose them at this moment. You just compute the multipliers from here. Yeah. Actually, the first step you very often do even a full step with the multipliers, but this is a detail I will just omit. But what we do now is actually we set delta lambda k, so the step that we would do in the multipliers, after one of the next iterations, it will be actually lambda tilde k minus lambda k, which was the previous iterate. And yeah, at the very beginning, you would set this thing, of course, to 0. I omit this detail, but let me just state a few things, namely that now you choose a step length. So we call it tk, which is element in 0 and 1. Perfectly would be 1, but we choose it by some line search. Yeah? And this line search we discuss later. So you have a line search here to be discussed. But then you do a step. And the step is, of course, just taking xk plus 1 equals xk plus pk. Actually, pk times tk. And you could also update your multipliers and you say lambda k plus 1 is like the old multipliers plus tk times delta lambda k. And this is only one possibility for the Lagrangian update. The Lagrange multipliers, there is also the alternative formula possible where you just say lambda k plus 1 is equal to lambda tilde k. So you basically say what you got from the system, you directly do a full step in the multipliers. Yeah? So please note that if tk would be 1, then this formula would anyway be satisfied, right? But if tk is smaller than 1, then there's a discussion of what you do, and this is one option where you actually make your multipliers also move slowly. That's a choice. But what is now interesting is that in this typical algorithm, you would now compute the old Lagrange gradient at the new multipliers, and I will actually explain it in a minute. Why we need that old Lagrange gradient at new multipliers. So you compute actually this quantity, nabla L at xk and lambda k plus 1. And you compute it here because you need that later to compare it with the new step. In a BFGS method, we need to compare two different values of the Lagrange gradient, and in this BFGS method, that is one special case of this whole algorithm class, you will actually need this. So we should remember it, and it can just be obtained from the quantities that we have computed now. So these are all the quantities that we needed, right? So we have the gradients and so on we have from before, and then we have the new multiplier, and now we can compute this thing and remember it. And after we have evaluated it and we remember that, we start to recompute these quantities. Actually, we can use the same memory, so we can override them. And so now we do an evaluation where you evaluate these quantities at the new point. Yeah? So you evaluate exactly the same things that we had here. So it's actually now nabla f of xk plus 1 and g of xk plus 1 and nabla g of xk plus 1. So we compute all these new things that we need for the next iteration to prepare us for the next iteration. And after we compute them, we can compute the new Lagrange gradient at the new point. And then we say actually compute the new Lagrange gradient. And we call that nabla L, or we don't call it, but that is this thing that we need to compute now, lambda k plus 1, which is given by nabla f of xk plus 1 minus nabla g of xk plus 1 times lambda k plus 1. So please note that we have the same index for the multipliers for the two Lagrange gradients, and that this is important because later on we will use the difference of these two in order to approximate the derivative in x only and not in x and lambda. Okay, so we continue. This algorithm is a long one, so it takes about 3 pages, and we compute these two things. And what we now do is we need to choose a new Hessian. And so we have some alternatives here for BFGS updates. Yeah. So that's the one new thing. We would set SK to be the step difference, actually what we just did with our x's. So it's actually the step TK times PK, but yeah, just to be sure, it's this difference. And we also set YK to be the difference in these two Lagrange gradients, which is one k plus 1 at lambda k plus 1, and the other is at xk. But as I said, so these are quantities that we have computed before. Now we subtract them, and then we get sk and yk, and then we get bk plus 1 is equal to bk. And then how was the BFGS formula? Maybe you can help me a bit. I don't remember it maybe by heart, but I try my best. So it will be this formula, I think. Here we will have something with a plus, I think, and this would be sk transpose yk, if I'm not mistaken, or is it? No, yeah, I think this was yk, and then sk. Sorry, there's a yk, so it was actually multiplied, I think. You can help me. Yeah, yk and a yk transpose. Exactly, that's it. Exactly, that was this part of the formula. And here we had, I think, the difference, was it?
It's bk.
Yeah.
S is transpose bk.
Exactly, that's making sense. Exactly. So this was the formula, and we can always check it briefly. If we multiply that thing with an sk from the right side, this gives bk sk. This gives also bk sk, but with a minus sign, because these two things cancel, so that is omitting, and then this is yk sk divided, so it gives yk, and the second condition is indeed satisfied. So what we have is, I just wanted to recall the basic property that we want, and which I sometimes use to remember if I have the right formula, is this, the second condition. But anyway, this is the BFGS formula. It gives you a new Hessian approximation based on the old one and on everything that we computed. And that is now an approximation of the second derivative of the Lagrangian in x direction, and that's why we were only allowed to perturb in x direction, and why the lambda should be the same here. Of course, we take the most current lambda that we have, and because we had already lambda k plus 1, we use lambda k plus 1. So you see, before we didn't need actually a multiplier at the beginning, because our first multiplier that we need is actually lambda 1. Okay, and then you set k equals k plus 1, and you end your loop. But, yeah. And why? So that's a very rough algorithmic sketch, which is a bit different from what we touched until now, because before we looked at metrics approximations which were not obtained by BFGS, but we looked at different ones where we would use this bk by Newton or by Gauss-Newton. Yeah? So let me just say that this is like the most complicated algorithm. Yeah? So this is like one variant, A. So this part. Yeah, so this is one part, but as a remark, I want to say that this A can be replaced by other things, and then you have a general algorithm for the methods that we did before. by several things. So maybe I call one of them B. B would be, you could actually compute the secondary, you could try to just compute really the exact Newton. Yeah? That means that you take bk plus 1 is equal to the second derivative of your Lagrangian. I should say this is always with respect to x, of course. And you could already evaluate it at the next point. If you have a tool available that allows you to compute second derivatives, plus positive definiteness. Check. So it's actually not only a check, but you would change the matrix a bit. If you detect negative eigenvalues, you would actually add something. For example, you would add a Liebenberg-Marquardt term or whatever. Yeah, so there would be many variants how to deal with non-positive definiteness, but this is one thing that you could do. That was the method that we discussed first, but we could also alternatively do C, and that is only if f of x is given by 1/2 some residual function, which is squared. And you remember what we discussed last time, that then also for constraint problems we could use bk plus 1 to be the the Gauss-Newton approximation of the Hessian, which will be based on the Jacobian of this thing. So the Jacobian of this thing at the newest point xk plus 1, and this, of course, the Jacobian. This is the Jacobian, and this is the Jacobian transposed. And this matrix here is positive semi-definite. In the normal cases, even definite. So this has full rank. It's positive definite, and so it's a very nice Hessian for this would be Gauss-Newton. And you see all these methods come under the same algorithmic frame. The main frame is always the same. You choose something like an initial value for the Hessian. You need to have one at the very beginning in order to formulate your first system. Then you have your loop in which you first solve your system, then possibly evaluate your Lagrange gradient, evaluate the difference, use it for updates, or if you don't do that, you can also get the exact Hessian or the Gauss-Newton Hessian. I think for programming purposes, this would be the easiest to program, the Gauss-Newton, because you don't have to first have memory of lambda, so you could make your algorithm much quicker actually, and write down it simpler if you only had this, but I tried to make it a bit like so that you could fit every different Hessian approximation here into this algorithm. So these would be the three variants. And I want to add one remark, which is something I want to share with you, but it's not something that we will implement. What we do here is actually assuming that we compute in this iteration matrix the nabla G, the Jacobian of the constraints exactly. And very often this is making sense, and for usually this is like what you want to do. But it's still a big Jacobian matrix and some problems which could be very costly. So there exist variants, and you remember Newton-type methods do not really require that you evaluate your iteration matrix exactly. You could actually do everything inexactly and not only the B. Here we do the B inexactly, but we could also do the... So here, bk nabla G of xk transpose and nabla G of xk is the approximate Newton matrix, right? So it's approximate because of the B. So maybe I call this MK, because it's the MK. Yeah? And you remember when we look at this Newton type framework, then we also had the true derivative. I mean, maybe I do a minus sign here. We also had the true derivative of the residual function at wk, and this would be the second derivative of the Lagrangian at xk lambda k, and here we have nabla g xk transpose and minus nabla g xk. So this would be the exact iteration. So this is the exact one. And if you compare them, and this is what we need to compare for local convergence, you need to subtract b from this one, and then the remainder was actually the difference only between these two things. And that's why we looked last time about the difference between b and this. Yeah? So the difference of the iteration matrix mk minus d big F d w wk. Yeah? So this matrix difference is given by bk minus the second derivative of the Lagrangian, and everywhere else we have zeros because we evaluate all the rest exactly. Yeah? So the conclusion here from this remark is that means the convergence rate will only depend on this difference. So the speed, so like linear or superlinear or quadratic, depends only on this difference. Only on the Hessian. Yeah, on the Hessian approximation. Maybe we call it Hessian approximation bk. So if that is close to the second derivative, then you can be very happy and have quadratic convergence and so on. But now you could alternatively say, why don't we also approximate these things? So there is no reason to say that that all entries in your matrix should be exactly the same. If this is anyway not the same, you could also say, then why do I not replace these things? Yeah? So alternative methods, which are not the main focus, alternative methods could also approximate the Jacobian. So this Jacobian is actually, what is it? So this nabla g of xk transpose, which is the Jacobian, you could also say I find something which I call ak, which is approximately the Jacobian. Like the Hessian matrix, it's not exactly the same thing. And that means they would solve linear systems with this matrix, bk, ak transpose, 0, and here you have the vector pk, and here you have something which we call minus, and I will specify that in a minute, actually minus delta lambda. Okay. And of course we need to also think of what is the residual that we need here. And if we want to do this, then our Newton matrix will be different from the true matrix. And there is, in principle, no problem with this, because we could always do it, right? So you remember in exact Newton methods, they could use any approximation. It need not be exactly, as long as the residual that we want to bring to 0 is exactly evaluated. But here's a little difference. If we want to make this method work, we need to have here really the Lagrange gradient at the current iteration. It includes the multipliers. And of course we also need our constraints to be evaluated correctly. And what you see here is a bit funny. So you see here I need the Lagrange gradient, and I cannot do this trick that I take the next multipliers, the absolute values anymore, because this matrix is not the same as this, and we needed that, right? So in order to be able to make here the objective gradient, we needed the fact that this thing times that would be exactly the term that was part of the Lagrange gradient. I don't know if you remember that. But so this method would now need the multipliers and also the exact Lagrange gradient in order to be able to converge. And so this is a bit confusing if you think of Yeah, so remember that nabla L at xk, comma lambda k is nothing else than nabla f of xk minus nabla g at xk times lambda k. Yeah, so that was the definition of the Lagrange gradient. So you could say this is a stupid method because it needs to evaluate this derivative anyway, this Jacobian, right? In order to compute the residual, and then it throws it away in order to use something which is only worse, yeah, namely something which is approximate in the blocks that you need here. That sounds like a stupid idea, and for this reason it's also not so widespread. But the funny thing and the really interesting thing is that it's not true that you need to evaluate this nabla G, this full matrix, in order to compute that thing. Because with adjoint differentiation, you could just say there is a function, that's the function lambda of x and lambda. And this function you can differentiate with respect to x with the adjoint mode of automatic differentiation. And then you get this gradient with a cost which is just 4 times as high as the cost of evaluating the Lagrangian. So in principle, this function here is easy to write down. And if you just differentiate that function with respect to x using the adjoint, then you can avoid the explicit computation of this quantity. Can be differentiated by reverse AD to obtain nabla L without ever computing the full Jacobian nabla G of x transpose. Yeah? So this matrix you don't need to compute for that method, and so this could lead to potentially cheaper iterations. So the whole thing is from this alternative method on, so this remark, these are called how do we call them? There are many ways for them, but sometimes they are called adjoint-based Newton type optimization methods. So that's the class to which this will lead, but which we will not cover very much in detail. I just wanted to make this remark because it's so easy to conceptually think about it. You could just take an iteration which evaluates these things exactly and then somehow gets approximations. And of course there would be different ways to get these approximations. One way is actually to just evaluate them once at the beginning, then keep them constant for a while. Another one would be to also do updates on these numbers, like we do updates for the Hessian. We could also use updates for the constraint matrices. And so there are many possible variants. And so depending on these things, they can also have linear convergence usually, or sometimes superlinear linear convergence if you actually update all the matrices. But mostly these methods don't give you quadratic convergence. Okay, I think I will not really get into the theorem again, but because we did it already in much detail, but the local convergence, you can see it directly from this fact, and the fact that it's equivalent to a Newton type iteration. If this matrix is actually getting, if it's anyway 0 because both are the same, then you have kappa equals 0 in your local convergence. If there's a persistent difference, like in Gauss-Newton, you will have only linear convergence. And if there's a vanishing distance, then you will get superlinear convergence. Yeah? So local convergence, and I will not bring that in form of a theorem here, will be. So first of all, for bk equals to the true second derivative, it will be quadratic. for BK equals, for example, this Gauss-Newton, so nabla R transpose, you will have linear convergence. And if you have the BK from BFGS, you will have superlinear convergence. Of course, there are some details I have to leave out here, but basically these are true statements. If you take the exact Hessian, everything is nice. If you take the Gauss-Newton, you get very often good linear convergence. We discussed it last hour. And from BFGS, you would typically get superlinear convergence. There are some details about BFGS that I will hopefully have time to cover. But before I want to come to that, I need to comment on the line search, because there was this big thing that we said, you choose a T. And I didn't specify how you choose a T yet. No? And if you think of line search, that's intuitive. We had that before. So we should just reduce a function, and then we find that it satisfies Amio's condition, and we do some backtracking. You remember that. But what function should we use? So you don't know exactly. You have an objective and you have constraints. The constraints might be violated. So there is actually not one function, but there are lots of functions that you want to bring to zero or that you want to minimize. I mean, the objective you want to minimize and the constraints you want to bring to zero. And so what happens if the constraint is getting better, but the objective is getting worse, for example? Is that an acceptable point, or what does it mean? And so there are different ways to tackle this issue. And the classical one, that's also a very useful one, is globalization by line search. And merit functions. And so you need to introduce a function that you call a merit function, because it's not the objective, but it's something that is related to the objective, but reflects the fact that going actually improving your constraints is also a good thing, yeah, to make it more feasible. So if you think of globalization, and the idea is that you weigh the constraint violations and you add them, so to say, to the objective. Yeah, so to introduce a merit function. So this merit function, it weighs objective and constraint violations. So, I should say that we are very much actually back in what you have as a script, I think. Yeah, so that's just to make some of you more confident. But this merit function could be, for example, one typical function that I want to define here, that is the L1 merit function. And it's a merit function which I call T1. It's a function of x. And this function will be consisting of the f, the objective, the objective we want to minimize, but it will also contain a sum, and this is a weighted sum. Wait a moment. Okay. A weighted sum of the violation of the constraints and the objective. And so I will have some now on the violation of the constraints, and I will somehow penalize it. And I choose here one factor sigma, which needs to be big enough, and I need to decide which norm of G I will choose. And a very typical one, and that's why this is called the L1 penalty, is that I use here a 1. So what you see is that this is something that weighs an objective function with a weighted sum of constraint violations. But even though I like to write this down in this form, and though it is actually seemingly making sense, it's also the way how it's presented in many textbooks, you could already see from this formula that this is not exactly what you want in practice, because what you do here is you add apples and pears, right? I mean, I add the objective, that makes sense, But here I add maybe a constraint, like I want to hit this point in meters, and another thing where you want to be something that should be exactly 5 kilo. Yeah, so you would actually add meters and kilos up here in the L1 now. So in reality, let's say, what you would actually use, or in practice, is something which is a bit more complicated to explain, but it's actually very easy. You would actually choose a function where you say, I have my scaling, I call it maybe S, inside my one norm with a matrix S, which consists only of diagonal elements which are sigma 1 up to sigma m, and it has nothing to do with singular values, but it has the same structure in the sense that these are all positive entries, and it's as many as we have constraints. Yeah? And each constraint would be weighted with something so that it gets the same units as the objective. So you see already that the sigmas have the units of the Lagrange multipliers, right? Sigma I positive and sigma I have something to do with the lambda i's. Yeah? So you can already get from the unit perspective that the units of them actually, maybe that would be the correct statement, the unit of sigma I, if you would work with units, which on a computer you don't, but anyway, it's still good to keep always in mind that things have units. That's one of the things I want you to really always look at when you have it. So you would in practice actually use this scaled version where you have one specific weight for every constraint. So let me just say what this T1, this practical one, looks like. It will be f of x plus the sum of all the constraints separately, I starting at 1 and m, and then each of these is multiplied with a positive weight sigma I. And so I can draw it inside or outside this one norm, but for notational convenience it's good to have it inside with this matrix big S, right? Then I don't need to write the indices, but this is what you should have in mind, and that's also how it can be implemented. Yeah, and so now the interesting question is if this merit function really helps you in globalizing your algorithm. And so there are some questions. The first question is, does a solution of your optimization problem, actually if you minimize the merit function, is it actually a solution of your optimization problem? It's the first question. The second question is if you generate one of these steps with that algorithm, does it actually help you to find a descent direction? Because if it doesn't even give you a descent direction, if you have a very smart algorithm that has locally nice convergence, but if you don't know that you go down, then you cannot do a line search because we need a descent direction of the function. So intuitively the first part, so two questions I should say. One is minimizing T1. Is it equivalent to solving the NLP? And the second is, does the Newton type method deliver descent directions? And you remember what was a descent direction? It was a function, a direction into, when you go in that direction, your function would go down. Yeah. And so now the interesting thing is, if you think of how such a function works, it will be. Before I argue about these things, I want to visualize. So imagine that you have, for example, one function f. That could be a nice quadratic, for example, like this. So that's f of x, and here's x. Yeah? And then you have another constraint function, which could be the constraint that you want to bring to zero, that turns out to be something like this. Yeah? So that could be g of x. I visualize this without any other constraints. So what will be g modulus of x? So if you take the positive part of this, then this part will be mirrored, of course. So it will be looking like this. Yeah? So then this will be g absolute value. I think you agree. And on the right side, it's also the absolute value, but it doesn't change. And now if I multiply it with a positive factor, which is big enough, so let's make it a bigger factor, then I would get actually this function here. So I scale this up with, let's say, for example, 2. And I get this and this, right? So this would be sigma times g norm. And so you can imagine if I make it bigger and bigger, then this is actually really making it impossible to go away from this feasible point, and because all the other points are penalized, so on. And so the resulting function, so this T1 function, will be, of course, the objective plus this thing, and at the point where the constraint is satisfied, it will be the same as the objective. But on all the other points, it will be of course, there will be something significantly added to it. In this case, these terms that I have here. So I just add this and that function together, and I get something that goes more or less like this function. And yeah, I don't know exactly. It will actually be more. Yeah? So something like this. Yeah? I don't exactly know how to add these two functions. And here I do the same. I think the curvatures are nearly the same, so probably I get something. This is going a bit down. So it will go slightly less down. And I guess it looks pretty linear, so like this. Yeah. So that would be the addition of the f and the yellow curve, and so this function will be T1 of x. Okay, so you get a visualization of how such a merit function looks like. It is a non-smooth function, so that's an important point. And it is a function which depends, of course, very much on this penalty parameter sigma. And if you make it bigger, you will actually make it nearly impossible to go away from the feasible set. And it turns out that because the only thing that could drive you out of this is if the gradient here, if the gradient of your objective would be stronger than the gradient that you get here from the penalty function. So if you make it big enough, you will always be able to dominate the gradient, and the minimum of the merit function will be also a minimum of the NLP, and the other way around. Yeah. So what I want to say is for sigma I big enough, so all of them, and we need to specify how big is big enough, but it has actually to do exactly with the multipliers. Minimizing, so one is true. And so then minimizing T1 is equivalent to solving the NLP.
What
Yes?
is it to change of shape, this miniaturization? Where does it go?
So what do you mean by change of shape? I mean my objective function is this nice shaped thing, and then I add this thing to it, and so it gets the addition of the white and the yellow curve is the blue one. And the addition might look a bit different, but here I looked at it and I see that here the curvatures are nearly the same, so that's why it remains linear. And here I think this curvature, also they basically, that's just how I plotted it. I should say that if for example, if you have a two-dimensional problem, things get much more interesting, but I couldn't draw them on the table. But in that case, this constraint would still have a full set of possible solutions, and it's creating actually a ridge. So think of, for example, just another example. So what would be if your constraint is x1 square plus x2 square minus 1 equals 0? So that's actually g of x. And so how would now this function look like if independent of the objective? So what is actually this thing? So how would it look like? Yeah, just the norm of that thing, and it will look like something, and this is difficult to illustrate, but I will first do it actually here on the two-dimensional plane. So these are the feasible points. on the feasible points that this function will be 0, of course, yeah? But everywhere else it will go up. So it will be higher here, it will be positive, and here it will also be positive. Yeah, so it has a minimum, but the minimum is just a circle, and if you would like to draw it, I try to do my best now with a two-dimensional drawing. So this is x1 and that's x2, and here I could draw it like this, x1 and x2. Now they are in the plane, and what I would have the circle here. Okay, so this is the circle, the function is 0, and then it goes up, and here also it goes up. But in the middle it also goes up. Yeah, and then what I get is actually circular lines. So I get, so to say, a cylinder in the middle and something here at the outside which is also cylindrical. So I get a valley that is quite difficult to draw. But I think you get the intuition. So here's actually the valley. Maybe I draw it in yellow. So here's a valley, and the same valley would be exactly here. And then you go up. And so, of course, the crucial thing is on the feasible set, it does not change the objective. Yeah? So that's why it's of course, keeping things equivalent. So this was a heuristic, but not a proof, but the minimizing T1 is equivalent to solving the NLP if it's high enough, and it turns out that it needs to be higher than the multipliers. Yeah?
There is one value for sigma and
yeah.
then it's equivalent,
yeah.
And not just with the line.
Sorry, if it's big enough and if it's bigger than this one value, then it's still equivalent. So you can make it as big as you like, but it just needs to be big enough to make them equivalent.
I thought it was like you have to increase sigma and every iteration or something.
Yeah, in practice you don't know how big, and that's why you have to adapt it. But in principle, yes, at the moment we just assume somehow magically we get these weights, and if we have these weights we have a merit function, and if these weights are high enough, then we can actually say, let's try to get downhill in this merit function, and then we have a guarantee of going down. And that's actually the basic idea of line search questions. But there is another question, and that is actually if it does really deliver you a descent direction. And before we can even talk about descent directions, descent direction was some function, direction where the derivative of your function would go down. But now we have a function which doesn't have a derivative everywhere. So if you think of this function here, it's a non-smooth function. So at the points like this point, you don't have a derivative. So what do we do about it? And so the beauty is we can generalize the notion of derivative to directional derivatives, and that's what we need to do here. And then we can actually say and define what is a descent direction. Okay? So I will. Who is aware of directional derivatives for smooth functions? Okay, a few, not so many. Then I suggest that we do it after the break, because otherwise I'm in danger of rushing too much about this important topic. So let's do a 10-minute break. After 10 past 9, 10 past 3, we continue. Okay, so I would like to continue. And as promised, I want to define a directional derivative of a possibly non-smooth function. So it could be a function which can have kinks, like the L1 penalty, or the L1 merit function. So we are still in chapter 12.3, 12.8, sorry. And I want to add one thing before I do, that this term that we add to the objective is sometimes also called a penalty function. Yeah, a penalty function. So this s times g of x in the one norm, that could be a penalty. That's sometimes called a penalty function. Yeah? Because it penalizes every point that's not feasible. And so the T1 is usually called the merit function. But it's actually equal to f plus the penalty, right? Just that you get the relation between what people call a penalty function and a merit function. The merit function actually should measure progress, and we said already if it's having high enough penalties, then actually it will measure a progress in the sense that the solution of that function, minimizer of that function, will be also a minimizer of the original problem. But now we want to deal with derivatives, and so I want to define a directional derivative. Yeah, directional derivatives. And these directional derivatives for some function, so we have a given f from Rn to Rm, so some function, and it will be continuous, and actually it should also be Lipschitz continuous. And we can then try to define a derivative, and we say actually df at the point x in direction p. So p is just a vector in Rn. And that is the vector in which we want to differentiate that function. And then we say this is defined by a difference quotient where we say let's move in this direction p, subtract the value at x again from it, and divide by t. That's the usual thing that we use for difference quotient. But let's do this only for t's that are bigger than 0, and t is actually going to 0. But only for positive values. So it approaches 0 from positive. So it's not actually just t going to 0, but it's positive t's only. So you actually allow only to perturb into the direction of p and then to go back, but you don't allow to go, for example, in the negative direction of p. And so to give you some example, what would be now if your f of x is given by, I just take a simple non-differentiable function, x minus 1, absolute value. This function looks like this. Here's x, here's 1. So that would be the function, and now at any other point, it doesn't matter what you take. It's actually the same as the normal derivative multiplied with a p, of course. Yeah. So at most points, it's just the derivative of this smooth part. But at this point, what will happen? So if you think, for example, what would be df at this point 1, so x is equal to 1 in the direction, and you say, for example, 2. 2 is positive, so I will actually perturb in the positive directions, and okay, I can just do the definition, and I will have x minus 1 plus 2 times t minus x minus 1, right? So that's what we have here, divided by t. And then I should have limit t to, let's say, 0 plus, then I keep in mind that it should be positive. So here I have 0, and here I have 0 as well, because here's 1, right? 1. And 2 is from here. And so what I see is that it's actually 2 absolute value of t divided by t, so actually this is always 2. Clear. If it would be 15, then the result would be 15. Yeah? But now I could take a negative value at the same point, and let's say minus 3, for example. And then I get here the same thing, but here I have 1 minus 1 minus 3t minus 1 minus 1 divided by t. And what I see here is actually that I get 1 minus 1 is actually, it's minus 3 norm. Independent of t, by the way, because it's a linear function. But this is actually equal to 3. So it will be positive. And that's exactly what you would expect. So in this direction, even though when you go to the negative direction, so this is actually minus, that's the minus 3. And this is the plus 2. In both cases, you go up. That's very different than so it's a two-sided derivative. It will be different depending in which direction you go. Yeah. So it's dependent on direction. On direction and size of p. That's a fact about these directional derivatives. And directional derivatives are now what will replace derivatives when we deal with merit functions because they are not differentiable. But then the rest is the same. So we could actually say that we get a descent direction if the merit function goes down, right? So let me just define. P is descent direction. It's a descent direction for t1 of x if and only if the derivative of this function t1 at the point x in the direction p is smaller than 0, like before. Yeah, just before we could write it with a nabla g transpose p, that was the directional derivative, but here we need to have this more clumsy notation, and that's why we need it. So I want to have a note so that you just are aware of this. For any f element in C1, so if it's once continuously differentiable, we have, of course, that df at x in the direction p is given by nabla f at x transpose times p. So that is exactly the formula that we used thousands of times already, but for non-differentiable functions, we need to have this more general formula that we can, of course, we can sometimes go back to this definition, but we will also sometimes try to get it, to get more elegant ways to compute these derivatives. So what I want to now show is that actually the step that you get from solving a Newton system with exact derivatives for the Jacobians and with positive definite Hessian will give you a descent direction. So that's what I want to prove. And so the two things I want to prove is actually, I first say what I want to prove and then I prove both things. So the first thing is a lemma that I call lemma 12.4, and this says if P and lambda tilde solve the system actually, and what system should they solve? They should solve the system which has the gradient of the objective, nabla f, at x, and here the constraints at x, plus, maybe I do it even, I think I omit the index x, because that is not necessary here, and here I have the exact Jacobian, so that is important here, and then here I have the exact Jacobian transpose and a 0. And here I have p and minus lambda tilde, so like the thing that I had before. So if they solve this linear system, then there are two properties that hold, and the first one is actually a step to prove the second one, but I will just do them one step after the other. So let me say, this is actually that the direction derivative in this direction p at the point x at which we solve the system, at which all these derivatives are evaluated, that this is given by the gradient of f at x transpose times p, something that we would expect, then minus the s times g of x with a 1 norm. So from now on, I think I will extend and I will adapt a bit my notation to this scaled version where all my weights are on this diagonal matrix big S. Yeah. So the second statement, which will build on that, is actually that the same derivative can also be expressed as something like with an inequality, that this is actually smaller than minus p transpose b p, and then minus, and this is something I need to adapt, and that is actually S minus, I need to define a matrix that is actually called lambda, and this matrix I will define in a minute. Times g of x, and then here it is the I think the notation will now get a bit more clumsy. So this is the little thing I didn't consider. but we will manage it. Wait a moment. I will have this thing, yeah. And let's just do it this way. I need to define what this lambda is, but I think this is not the right way. I think I need to pull it out. So sorry for this confusion. I need to adapt my lemma a bit to this new notation. Didn't think about it carefully enough. So let me just state it in a form where I say maybe I do it, I call it S modified times, I write it in vector, not in vector notation. Why will I write it one constraint after the other? That makes more sense. So I have here my sigma I minus lambda I norm times g of x, gi of x norm. So this is what I want to prove actually. And what you see here is that if this would be a positive definite matrix, this would be positive, and then the whole thing would be negative. And so if this also would be, this is positive, but if this thing would be positive as well, because the sigma is bigger than that thing, the multiplier, sorry, here it should be lambda tilde, by the way, it's the corresponding multiplier for that constraint from that solution. If that's also positive, then the whole thing is negative, and then the whole thing here is really smaller than 0. And so the corollary, before I prove this theorem or this lemma, the corollary is what we really want, and that is if B is positive definite and S is and S sigma I is bigger or equal to the absolute value of lambda I for all constraints. Yeah, so if this is the case, if it's really bigger than the corresponding multiplier for every single constraint, then P is a descent direction for T1 of x. So we will prove it in a minute, but let me first discuss what this means or why it would be useful. So if the P is positive definite, that's something that we can ensure. And if the sigmas are bigger than the multipliers that we got from the system, this is something that we could actually adapt if necessary. So we make the sigma just big enough. And then we know that P is a descent direction. That means it leads down in this T1 function. So that means if we move at least short enough, then we will always get improvement. So we could impose an Amio type condition and so on. Let me prove these two things. And I think the proof of the corollary is immediate. I think I did it already. I mean, if this is positive and this is positive, and because of the two minus signs, then this whole thing will be smaller than 0, and that was the definition of a descent direction. Yeah? So in that sense, it should be strictly smaller than 0, and so that is exactly what we want here. I should say if P is not equal to 0, right? So there could be a solution where P is 0, the lambda is not 0, and then it's not a descent direction because it's just not moving. But if it's non-zero and these two things are satisfied, then it is a descent direction. Are you on board? Half? Okay, so I want to prove these two things, and they go in two steps. So I will prove one first and then two, and as I said, the corollary is already proven, right? So the first thing is we need to somehow compute this derivative into the p direction, and we could just use the definition. And so what I want to start with, I want to just evaluate this function at the direction valued in the direction p. And what is this function? It will be actually f x plus tp plus, now we have this notation with a sigma times g of x plus tp. One norm. This was our function at the new point when we vary t, and of course at the end we will let t go to 0. But let me complete that with a Taylor series. So I could actually say this is can be based on a Taylor series where I put f of x plus nabla f of x transpose times p times t. So p is a vector, but t is a scalar. That's this Taylor series. Of course, we need to have plus o t squared, so we will have some terms of higher order, but I omit them. And then the same we can do here. So also here we do a Taylor expansion. And so what we do here is actually we get plus s times, and then I expand this g of x plus nabla g of x transpose times p times t. And then I take the one norm. So that is also something where I omitted a term of second order in t. Yeah? So now the nice thing is that I can replace this thing. I mean, one part of this equation, and I just write it here, is this equation. G of x times nabla g transpose times p is equal to 0. So we know that g of x plus nabla g of x transpose times p is equal to 0. That means that this term is actually equal to minus g. Clear. So when I have this term, I could just replace it by minus g. And that's what I will do. So then I will actually say this is actually f of x plus nabla f p times t. So this is like the thing I have. And then I have here plus. And now it gets interesting. I will have here a 1 and here a minus t times g. So what I can actually do is I can say I have 1 minus t times s times g of x. And I take here the 1 norm. Actually this part was inside. Yeah, so I didn't do any change. It's exactly the same thing. And of course, the second order terms are still here. But because this is, if the t is smaller than 1, which at the end it will be, so t is bigger than 0, but t is smaller, actually much smaller than 1. Yeah, so we will actually look at small t's later. I can pull it out because that's a positive number. I hope that you agree. So because this is minus g. And then I have 1 minus t times minus g. And then I pull that out. Okay, and that was already the crucial step, because now I get already something I can recognize that this term, together with this term, with the 1, is actually the L1 merit function. So that is actually t1 of x. And then there are remaining terms, which is this term, nabla f x transpose p times t. But then there's also the other term, which is this thing, which is also with a minus t. So I will actually bring them together. And here I have s g of x, 1 norm. And this is times t. And then it's plus o t squared. And now I have it. I subtract this thing from that. And then I divide it by t. And I neglect second order terms. And then I get this as the derivative. And that is the formula that I wanted to get. Okay? So that's the first part proven. Yeah? The crucial step from here to here? Yes. I will do it. I will really do it on the new blackboard, then I have more time. So actually, the point is this thing. I have the term s, g of x plus nabla g of x transpose times p times t. This is the term that I want to somehow simplify. And I use the fact that this is minus g. So I can actually write it the same thing, g of x, and here for this I write minus g of x now. That is the same thing, because p solves the system. So this is now what I have. Does it already help? Or maybe I do one more step, so then I get actually s, and here this is now actually g of x, but multiplied with the vector with the number 1 here and with a minus t here. So it's this. But because that is a scalar number, I can pull it anywhere, actually before or after or wherever. It's just a scalar number, so I can also pull it out of the norm, and then I will get sg of x 1 times 1 minus t. So that would be still a correct statement for any value, and then because it's positive, I can actually omit this norm. So this is sufficient for this step, right? Yeah, exactly. It was a bit too quick to do it. Yeah, so it really helps to have it in detail. Thank you for the question. So now we have done already the hard work. So now we have an expression for this derivative. And the interesting thing is, and that's actually important to note, the derivative is, of course, what you would expect, a combination of how you go down. This is the direction of the objective. But it's also somehow, because your step will make your constraints, actually tries to satisfy your constraints, there will be already this downhill step. This is always negative, right? So you see already that there's something negative because you try to improve your constraints by solving this linear system. So this will actually help us, and now we just need to get to the second step, and the only thing that differs from this and this is actually the same. Yeah, so it's just a different way to write that. But so we need to get this and this. And so for this I want to basically expand this nabla f transpose p, which we also get from this equation. So we use now, so we need to replace nabla f of x. So this is now the proof, let's say, of 2. So now we go on with the proof. And for the proof we use the first condition, which says that nabla f plus b times p minus nabla g times lambda tilde is equal to 0. So that's the first equation which we know will be satisfied, right? And so what we can do is we can multiply this equation with p and then bring all the terms which are on this side, we can bring them to the other side. So let's multiply the whole thing with p, so with a p transpose. That's what we do. And then we bring these two terms to the other side. So here we have it already, the first side. Then this thing will be minus p transpose bp. We brought it to the other side. And here we have now a plus sign. And that will be now, I can actually also transpose it. And I like to transpose it. So I will directly write lambda tilde transpose times nabla g at x transpose times p. So I didn't change anything. I just expressed it using this equation that I have satisfied my system. But the beauty now is that, again, I know what this is, right? That's what we used before. So this will be actually minus g. So I can directly write minus p transpose bp plus, with minus lambda tilde transpose g of x. Same trick that we did before. And that we have already done most of the work, because okay, don't worry, it's already over. So the noise is already over. So what we wanted to show is that we get smaller than something, and we don't know exactly what the values of these multipliers will be. They can be positive or negative. But if this is positive definite, that's where we want to go, this will be already negative. This one we don't know. But what we know is that this whole thing will be smaller than what happens if we take the absolute value of this whole thing, right? Plus the absolute value of lambda tilde transpose G of X. That would be one extreme way to deal with it, right? Just take the absolute value of that. But that one we also know is smaller than if we would take the absolute values of these things separately. And this is where we can go on. We could also take the sum of all these values, lambda tilde I and gi separately. And that will be surely also bigger than this expression. So then we have an upper bound for all our, for this product. There might be tighter upper bounds, I should say, but anyway, this is now an upper bound. And we have this. Because now we have actually, this thing is smaller than that plus this, and that's exactly what we have here. Do you agree? I mean, I just plug, putting nabla F transpose P into 2 gives the result. Into 1 gives result 2. Okay, so we have proven that we have a descent direction. And I realize that we did not even arrive at the end of the equality constraint optimization chapter today, because I wanted to tell you so many things. There is one thing that I want to just mention, because I want really to start with equality constraint optimization next lecture, so I will have to have some sacrifices here. And the sacrifice I make is that I limit to 4 minutes the next section. Just wanted to tell you about it. Yeah? So the next section I will only summarize. It's actually 12.9. It's called about careful BFGS updating. And I just wanted to point out one little thing, and that is that in case that you have these BFGS methods, it might be sometimes that that the Hessian matrix is not positive definite. So how to ensure that BK plus 1 is really positive definite in BFGS methods. So that is the question that we want to investigate briefly. And there are two things that are interesting, and there is one thing that we will not prove anyway. The beautiful thing is that there is a property which is inside of BFGS, we call it 12.5. And this lemma says that if you start with a positive definite one, so if you start with a positive definite matrix, and if some condition is satisfied, namely that yk transpose sk is bigger than positive, is bigger than 0, then bk plus 1 is also positive, yeah? And from BFGS. So it's the same formula that we copied on the blackboard before. So that's something we will not prove, but it's an interesting property, because if this is the case, so if it was positive, and if this condition is satisfied, then it's okay. So we need to only make sure that this thing is positive. So only need to check yk transpose s is positive. And so the funny thing is that this is something that is also absolutely necessary for the second rule to lead to a positive definite Hessian. So there can be actually, if this is not the case, then we cannot find any update rule that leads to a positive definite Hessian and has the second condition. So on the other hand, there's another lemma, which we can even prove, and that is saying that if sk transpose yk is smaller than 0, and the second condition is satisfied, bk plus 1 times sk is equal to yk. So this is the thing that the BFGS update and all other update rules should satisfy. So if these two things are satisfied, then bk plus 1 is not positive semi-definite. It will have actually a negative eigenvalue even. Yeah? So the proof of this is extremely easy. So you could also, you just take this formula and you multiply it with sk from the left side, and then you get sk transpose yk, and that was by assumption smaller than 0, and then you see that there is a negative curvature direction in your Hessian. Yeah, so in some sense this is, these two lemmas are very related. This one is something we can prove easily. It holds for anything that satisfies this. That's a positive property of BFGS that we do not prove, but, which is, for example, given in Nosedal. And so now there exist schemes, and this is what I only wanted to mention, which are due to Mike Powell, one of the pioneers of nonlinear programming, and he did a lot of tricks, and one of these things is Powell's trick, which I want to mention, or which is sometimes called damped BFGS. And the idea is if yk transpose sk is too small, actually it will be even for small, very small but positive values, you say it's already too small. Yeah, I will not specify it. Then modify yk before applying the BFGS formula. And what it will actually do, it will modify yk will become a yk tilde, so that the sk transpose with this yk tilde will be equal to something like a fraction of your old Hessian multiplied with s in both directions, and that means that actually this term here is positive by something like a factor of 1/5 of the direction of curvature that we had originally in the Hessian, so we can actually only reduce it by a factor of 5 in every update. And how to compute it, I will not give here. Details, script. Sorry? It's 0.2. It's just, I mean, this is a number that is arbitrary, but it's between 0 and 1. Yeah, it should be not too small, not too big, so that you allow some reduction in the eigenvalues, but you never go below 0. Okay, this is the thing that I just wanted to mention here, and it would be a modification that you could use, and which is sometimes called damped BFGS updating, or I call it also Powell's trick. So these are names that you can give to this quantity, and now I think I should stop, and next time we can really start afresh on Tuesday, next Tuesday actually, to have the last lecture before Christmas on deriving optimality conditions for inequality constraint optimization. I'm sorry if this was a bit fast, in particular at the end. So please take your time to digest it, and I wish you a wonderful weekend now.